Yeah, I think it's good to have it. We put it everything in one place and then
It's it's good grief.
all right.
Oh well, we don't really need the transcription. All right. Gonna sign in with this. Yeah, so basically what I'm doing today is I am going through sort of a quick and dirty version of my analysis process. So what I was going to do is I was going to talk briefly about what a GLM is. Because I don't know about y'all, but I did not have the best statistical education in grad school.
Yeah,
and I had to figure a lot out by myself.
Yeah, like an introduction will be great because most of the students, especially in computer science, they don't have like a strong stats, right? And sometimes like a GLM is not something that they actually use at all.
That is correct. Yeah, sure, that's fine.
But I was telling Rainy, the GLM it was the most powerful tool that we had before machine learning, right? Because
Yeah.
basically you can code any other stats using a GLM. That's the point. It's general, right?
All right. Now I'm going to launch desktop so that I can go into it later. All right. So. Yeah, should be. So first off, a GLM is short for general linear model. And it's basically a way of expressing the relationships between different variables together as a single linear equation. And from this, we can derive many different kinds of statistical tests, t-tests, ANOVAs, ANCOVAs, f-tests, all sorts of good stuff. Linear regression, obviously. Not to be confused with the generalized linear model, which is a fun thing to try to keep straight in your head. We're not doing those. But basically, I already said that. The base equation here is very familiar, I think, to anyone who's done any linear equations. So y is our, I left my pointer at home today. Y is our observations. So in this case, the MRI scans. And it's an array of all the scans that we've taken. X is the design matrix. So that's saying these are the variables essentially that we want to look at and determine sort of the relationships between. B is the sort of the slopes or the weights of the linear model that you're creating. And then U is basically anything left over after you fit the model, basically sort of an error term. So we expand this out. So you can see this is how it's expressed as linear algebra. So I labeled the different variables as different things. So for example, the first two columns might be saying which ones I wasn't expecting better. Which subjects are control, which subjects are patient. And then the next one might be age, ICV, those sort of things. And then the betas here are the weights associated with each of these columns. So beta A is the weight associated with the control subjects, beta B, the patients, and so forth. And then another term for these, for the sort of error term on the end, is residuals. So when you multiply it out, it comes out for each scan, you wind up with an equation like this, where basically everything is a linear combination of the various variables. Yeah, absolutely.
Yes, so for example, if one of the variables, just say age.
Yeah.
And we don't know if it's linear relationship between the variable from the observation. Maybe it's a quadratic form was it, how are we going to apply it here? Or we don't even know like how they are related. So
We are making the assumption that there is a linear relationship because,
so it has to be, that assumption has to exist, or
yeah, that is the basic assumption.
Yeah, I mean,
Of a
we know-
GLM.
we know that reality is not linear.
Yeah.
Right? But also, if you don't have enough information or evidence to tell you that there's a quadratic relationship, I mean, there's no need to go that far. The first thing to do is just to feed a linear model and see how it performs, right?
Yeah, it's like if you're creating an SPM, you might start out with a linear kernel and then see if you have better fitting with a Gaussian kernel or something else. So the other main concept with the GLM is the contrast matrix. So this basically is how we once we've run the model and we've come out with our betas, with our weights, this lets us then select for, all right, which factors are we actually interested in the relationship between? So the simplest way to use it is as sort of a variable selector. So I did a slightly more detailed version of a design matrix here. So we've got the first three subjects are controls. These are their ages, and these are their intracranial volumes. And then the second three subjects are patients. These are their ages. These are their intracranial volumes. And so what I've done is you see where the colors are matching. With the contrast matrix, what I'm saying is, all right, I want to see where the controls have a higher measured value. In the case of what I'm doing, it's volume in a voxel, where the controls have a greater value than the patient. And then conversely, with this second line, we're seeing, all right, where do the patients have a greater value than the controls?
So here, this contrast basically is when you specify what is the output that you want from your comparison. Right? This is not the model. The model is already created, right? It's the first step. Everything is calculated. You have all the data for every variable, but the contrast is like, okay, I want to do some comparisons,
Yeah.
right? This case, there are 4 columns, but if you see the zeros means that the age and the ICD are controlled, right? So what you are doing is that you are taking this variable and regress it out from the comparison.
Yeah.
Right? If you want to actually compare without this controlling variable, you need to put 1 in those columns. So they basically, that means that imagine that you have your two groups, but you don't know the age or the ICD. You could do a linear model, and then you will have the same contrast, the blue and the orange. And that what it's doing is just comparing directly your 2 groups, right? When you add the age in the ICD, for example, in this case, adding the zeros in these 2 columns, what it's doing is controlling for the age and controlling for the size of the head. So the comparison is better, right? Because you are including more information in the model.
Yeah. So basically, like where this C comes in is it gets multiplied by the beta and some other things. I'm not actually going to bother getting into the math of how you calculate the t statistic because it's not that important. What is important is that the C value essentially is what is used to select which relationships you're looking at. So like if we wanted to know the linear correlation of age with our output, then we would put a plus or a -1 in the black column. A +1 would be a positive correlation, a -1 would be a negative correlation. You'd check those separately for significance. Same idea with the green column if you want to know if there's any correlation between ICD and our volume. You would do that. But usually, but these 2 specifically I picked because we control for them. Yeah, so through a bunch of math that I am hand waving away for the sake of everyone's sanity, including my own, this is what gets us our t statistic. So it's just like in a t-test, you're going to get a t statistic, and that has some sort of relationship to significance. But with an MRI scan, we have hundreds of thousands to millions of observations in a single image, right? And you've got to be able to account for those. So obviously you could do something incredibly conservative like a Bonferroni correction, but at that point you're only going to be able to find things where p is like 10 to the minus 10 or something stupid like that. So there are more educated ways of getting at that. But I was thinking of waiting until we actually got into the program so I could mention it. But there are ways of controlling for this without.
Well, just before we go there, so remember that every time that you use stats, we care about the p-value, right? So say, okay, 0.05 is what science says that is okay, right? But in the brain, a GLM actually is not taking one signal, but you're taking the signal or the values of each single voxel here. So this equation, actually, you run it in every single location. So if you have 30,000 voxels, that equation is calculated 30,000 times, right? That's exactly where the multiple comparison correction happens, right? Because Bonferroni says, right, like if you run one test, this is the amount of significance that you want. If you run two, you need to divide these to two, right? Because the probability that your hypothesis is wrong increases because you are testing two things, right? So now this will be 0.0, right? This is your new p-value when you run two, right? But in this case, 30,000. Well, you just have to put that number here. However, like Bonferroni is way too conservative because if we do this, this will be 0.0000000, and we won't find anything, right? So you use other methods that maybe Jason will talk about right now.
Yeah. Would you rather I just mention it now?
How about we have false discovery rate or family-wise, right? So
Yes.
there are two different, at least for imaging, they are the most common methods.
Yeah, so what SPM uses is family-wise error correction, which is an application of random field theory, which basically allows you to find related clumps of data together, and sort of finds a way to split the difference between just looking at a raw p-value and looking at something overcorrected like a Bonferroni would be in this case. And we'll see, and I can maybe point to some of the stuff in the outputs once we get there. But I also wanted to mention quickly what SPM is. It's created about 30 years ago now, but it's been continually updated ever since. I think the last update was about 2020. And it's a very popular MATLAB package for MRI analysis that you can expand with toolboxes. And two of the ones we use are the spatially unbiased infratentorial template toolbox, which is basically a very sophisticated and dedicated toolbox for analyzing cerebellar gray matter because it's very small and difficult to look at. And the computerized anatomical toolbox, which we mostly use for, I believe,
For segmentation.
for segmentation, yeah. And you can use this either with a GUI or with scripting. And the GUI can actually spit out the script for you if you want. So that is as much as I had on a PowerPoint, because the rest of this is going to be all practical. So I'm going to stop sharing PowerPoint and start sharing. FISA is in here. Excellent. I'm going to share instead this guy. So I'm going to connect to the desktop I've got running here. This is Massive, which is the Australian server. Oh, allow pop-ups. There we are. Which is the server where all the data I work with is stored on, because our collaborator is in Australia. That's where our part of the project is sort of run out of. So SPM, like I said, runs in MATLAB. The version of SPM we're using seems to work best in (22B).
Yeah,
I don't know that.
In Massive, they have different versions of the same software. So, for example, you can run different versions of MATLAB. You can load different versions of FSL, because some people use different things, right? So that's the difference of how you call it from the terminal.
So I'm going to add my SPM folder, and I'm going to go into one of my data folders here. I'm going to go into SCA1. Let me just delete that test folder and remake it. Just an empty folder for me to do the analysis in for today. So just going to run SPM. Shush you. All right, everything we are going to be using is in the PET and VBM section, because what I'm doing is voxel-based morphometry. Take just a sec. So this is what SPM looks like. This is your main sort of control panel. This is usually either a progress panel or a secondary control panel. And then over here is the graphical output, where you'll see the brain images, you'll see the statistical reports and whatnot and so forth. So what I'm going to do is I'm going to create a basic model. You've got a bunch of different options here. 1 and 2 sample t-tests, ANOVAs, all that good stuff. I'm using flexible factorial because we don't want a full factorial, because we don't need or particularly want like all the interactions that we're going to be doing. Because what I look at is, and I think I mentioned this in a previous presentation, I look at cohort, so basically control versus SCA. And then I use dummy variables for site to basically separate out each site and try to basically regress out site effects where I can. We've already done some of that mathematically. And then age and ICV are the last 2 variables that get included.
But here, the important thing is that you have the simple models. Like, for example, you can choose a t-test, and that t-test, basically you have 2 columns, right? Your patients and your controls, right? But in the case that Jason is also including other variables of interest. So he has, for example, site, right? He just showed us that he has age and maybe ICV. So now he cannot just choose a regular t-test, because the t-test simply will compare these 2, right? So he wants to create a model in which he can actually control for age and control for ICD, but also have a predictor for each site. And a predictor means that you will model the data differently for each site, so you can also control for difference that happen due to the scanner, right?
Yeah.
Because the scanner is taking different images, and each the scanner might give you different quality or different distortions, right? So you
Yeah.
want to control for that.
Basically, going back to this equation, by including all the sites and all the other covariates that we want to control for, we're getting more and more, go away, we're getting more and more weights here because it has to account for the effect of all those different variables. And so that's how it sort of removes the effect of those variables by having to account for them in the model and then not including them in our final calculation of what's significant. So for the design here, we have two factors that we're going to consider: cohort, which is the variable of interest, control versus SCA, and site, which is each of the different sites. So I'm going to name this one cohort. And I'm not going to mess with any of the other settings there. And I'm going to replicate that. And I'm going to call this one site. Yes.
The GLM on the FSL mostly.
Mm-hmm.
And there's an option for F tests, which for me, that was always a hard concept to grasp, and I don't know if you can explain a little bit. Like, why would you choose to have an F test?
I don't know what an F test, like, I know I've heard of an F test, but I've never used it personally. There is an option to do that when we get to running the contrasts.
Yes, it's usually.
Yeah.
Select if you want, but I never.
I think it's a matter of, from the reading I was doing, F, like T is like the square root of F or something like that.
The thing is, depending on the model, you are comparing different things, right? And to my understanding, the F test is basically also called omnibus because it's basically just making all the comparisons as one thing. And that gives you kind of like how the data is, what is the variance of the data for that specific model.
Yes, I noticed that it was mostly used for like ANOVA.
Yeah, because in ANOVA you have different factors and different comparisons, right?
Yes.
You have maybe like time and group and the interaction. But the F test will do a comparison across all of them.
Okay. All right.
I
Okay.
mean, this needs to be double checked.
Yes, it's just they never understood when to
Yeah.
use it and when not to use it. So. I
Yeah.
never used it.
I am still learning stuff about how to use certain specific statistical tests. So now we get to subjects. So here's where we specify the scans. Now, it's important to specify them in the right order because the first time I did this, I did them backwards. So in the Excel file, we have patients first and then controls. Patients are group 1, controls are group 2. So what we're going to do is we're going to specify the patient scans first and then the controls. So I'm going to go into SCA1 and smooth, and I'm going to pick, so these are different tissue types. MWP1 is the cerebral gray matter. MWP2 is all of the white matter, cerebral and cerebellar, and a bit into the brainstem. And then SEG1 is the cerebellar gray matter. We actually cropped the cerebellum out of MWP1 because we want to use suit for the cerebellum because it's better suited to it, no pun intended. So I'm going to go in here. And then this is just regular expression for everything. That is the recursive button. There we go.
Selects all the files in the folder.
Yep. And then we're going to go back to control, smoothed, MWP1, recursive, and done. So now it's just added the names of those 245 scan files to essentially it's creating a data structure that is going to save, and that can be passed to each step of the process. Then conditions is what are the values of our two factors. So in this case, we have, no, wrong. Opening it with a text editor. There we go. So the first column here is the cohort. So these are all patients, and the second column is the site ID. So in this case, it's site 6. And what's going to happen is when we put those factors in, it's going to create dummy variables like the ones you saw in the presentation. So when you have like a simple binary 1 and 0, that's called a dummy variable because it's basically representing a group rather than a value.
So everybody understand what the dummy variable is?
Yes, like that it has zeros and ones, so in this case, it only has one, so it's gonna fill up the other ones with
Yeah.
0 and 1.
Yeah, like in this case, for example, Jason has 6 sites, right? So you can call these like 1, 1, 1, 2, 1, 3, 4, 5, 1, 2, 6, right? It's one variable. But for the model, the dummy variable what it's doing is like maybe site 1, then you will have 1, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1.
Essentially,
Site 2, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and so on, right?
because if you treat the site number as a value, you're going to get all kinds of wacky stuff because it's completely arbitrary. It doesn't actually represent anything, whereas the dummy variables represent a group membership. So now you can see it's a 245 by 2. So we've got a set of conditions for each factor for each subject. And you can scroll through them if you like. But it's not very informative. Next, I want to specify the main effects. So this is telling it, all right, what do we actually want to add to the model? We've got our factors, we've got our scans. Now, what factors are we actually including? Are we interacting them at all? And I'm including both main effects because while I'm only actually interested in the effect of group, I still need to specify the main effective site in order to be able to include it in the model and remove it. So I'm including factor 1 and factor 2. And then covariates. So we're using it this way. The multiple covariates thing is separate and allows you to import text files. That's not how I'm doing it. Because this is how I figured out to make it work. So we're going to have 2 covariates here. First is age. Oh, nope, that's the vector. I just have these in CSV files I emailed over to simplify my life. But what we're going to see when we get to the scripting part of it is that you can make things even easier on yourself.
Yeah, there's always different ways to input the data, right? And you could put everything in one matrix, I guess, and then you can use the other option with multiple coverages.
Something like that, yeah. Basically, the code I have is derived from this way of doing things because I have everything in a data structure.
Yeah,
Yeah. There is an option to change the way you center the variables so it can be based on different factors. Like, so for example, if you have two groups where you know you're going to have imbalanced ages, if you include an age effect that is averaged just across the whole subject base, you might accidentally be including your group effect twice, in which case you would want to standardize them within each group. We're not worrying about that. We don't have imbalanced groups. We don't have significant differences in age. We don't care about any of that. So we're just leaving it be. The other covariate is intracranial volume. This accounts for head size, which obviously is very important for, it's very important just in general for VBM, but specifically it also helps account for any sex differences because men tend to have much larger skull cavities than women. Apropos of whether we use it for anything or not. So that's how we've included now our two covariates. So now we have all the data that we actually want in there. There's one final thing I'm going to add, and that's an explicit mask. Because in the smoothing process, sometimes you can have data sort of go out of bounds. So I'm just putting the mask essentially back on it in order to make sure that we don't leave the brain essentially.
Yeah, this means that sometimes if you don't put a mask, you will have your results and then you will see the brain and then you will have activity or no, it's not activity, but like
Oops.
differences that are outside.
Yeah.
Where there's no brain, right? Just because the data is smooth, so there's still data outside of the brain. But if you select the mask, obviously the result will be cropped. And that.
Yeah. All of this is hard-won knowledge through a lot of mistakes made in the winter and spring last year. All right, so we have all the pieces that we need to actually set up. No, actually we don't, because the play button, you will notice, is grayed out. Because I forgot to tell it where I'm storing my stats in the first place. The very first step I forgot. So we're going to put that in stats and test. So this is going to store, it's going to store a matrix file there, and that's what you're going to be pulling up in all the subsequent steps. Does anyone have any questions? Is anything confusing? Do you want to fall asleep?
No, I think it's possible.
All right. So before I hit go on that, I want to show you something real cool. If you go to View and Show.M code, this is going to basically tell you exactly how it constructs the matrices or the data structures that it moves on, that it uses for its actual calculation. And you can basically copy this code directly. And obviously right now it's got the names of all my files and it's got all the actual raw numbers in there, hard coded. But you can replace those with variable names. And I'll show you that in a little bit. Actually, no, you know what? I'm going to show you now. So I'm going to open, can't quite click on that because it's going to screw me up. Stats, no, scripts, stats, and SPM groupwise mod. That's the one. I have to be very careful with this because it's a little unresponsive, and I don't want to screw things up. So these lines here are literally the same as these 5 lines here. Copied directly over. The only thing different is that I'm specifying it with, oh, bugger. There we are. Is that I'm specifying it with a variable instead of with a hard-coded name. And same deal as you scroll down. I don't need you to highlight all that. Please don't. Thank you. As you scroll down, we've got our second factor, and we've got our main effects, factorial design, etc. So everything that's in this is also in here. And so once you know what those lines of code do, then you can customize it a little bit.
Yeah, this is good because once that you have your model, if you want to run different versions of the same model, I mean, you just need to change those variables and then you run it. You don't need to go and click and click and click and click and click. Right? You can just like make your script and run different models and different data. Right?
Yeah, like I've created a wrapper for this where basically, check that up. I've created a wrapper with some error checking so that I can specify at command line, okay, I want to run the groupwise analysis, but I only want to run it with subjects from Baltimore. You know, like if you're troubleshooting subject data or something like that. Or if you want to change where you get your scans from or what have you. This is just a wrapper around basically running the model, running the estimation, and getting the results that I want.
And that's usually the case, right? You set up your initial test or the initial model, and then it always happens that you come to talk to me, and then I say, "Oh, why don't you do this?" And then you have to go back and run it again. Or when everything is ready, you send it to the journal or to the conference, and the reviewer is going to tell you, "Oh, you should do this and that," and blah, blah, blah. Then you just need to go back.
Yeah. Or you do what I do and you wind up with 17 different plugins in your code, and eventually you have to go back and spend like 3 days refactoring the whole thing. One of those.
Yeah.
I recommend doing it right the first time, but I'm not very good at that. So we've set all that up. Now we're going to hit the run button. And so you can see now, this is our design matrix. This is what we were talking about before. This is the X that I was showing in the presentation. So we've got the dummy variables for cohort. So there's all our SCA1 subjects. There's all our control subjects. This is site 1. So this is ready SCA. So these are the SCA and control patients from there. These are the SCA and control patients from Campanus, etc. And then we've got age and ICD at the end. So that's how that connects. So now damn it. Oh, I hope my HDMI port isn't breaking. And you can say this if you want as a PDF or as a PNG or whatever. But I'm not going to bother. What I am going to do is I am going to show you what it has done as a practical matter right now, the only thing that it has done is it has created this matrix MATLAB file, which has all the information I just put in, all the file locations, all the data points, all the specifications of the model. And now what I'm going to do is I'm going to go back to the main menu and I'm going to tell it to estimate the model. So now you select the matrix file that you just created, stats test here. We have the option of writing out our residuals, those error terms that come at the end of the linear equation, and that can be useful in some circumstances, but I'm not doing it here. So I'm just going to go ahead and hit run. And this is the part that is going to take a couple of minutes because it's got to run the estimation. It's got, I think, 11 or 13 variables in the design matrix. 13, there we go.
But you didn't need it to run it because you already have one, right?
Yes.
So,
Where do you put your contrast matrix?
That's next. The reason why I'm doing this sort of in real time is to show how it works in real time.
Okay.
So the next, while that's estimating, once it's done estimating, we will be going to the results. And that is where we're going to specify our contrasts.
Just make sure I understand this correctly. So this estimation is calculating the weights and bias?
Yes. Yes, that's exactly what it's doing. And it will write out the betas, it'll write out those weights, whatever you want to call them. And then, like I said, we had the option to write out the residuals as well, but I said, nah, I don't need that. And what comes up in here will be, some of those are going to go away once it finishes, but you see there's beta 1 all the way to beta 13. That is the B matrix from the presentation. That is beta for variable 1, beta for variable 2, beta for variable 3, etc. So that's beta for controls, beta for subjects, beta for ready SCA, etc., etc.
well, he finished, or
It has.
it's done. Okay.
It has finished.
It didn't take that long.
It,
I thought that,
no, I was expecting it to be much longer, but I think I got used to SCA 3 where there's 3 times as many subjects. So now you go to results, and it's again going to ask you for the .mat file. Because that's sort of its reference point for everything. And you see it's got the design matrix over here. So I'm going to define a new contrast. This is where you can tell it if you want to do a t-test or an f-test. What I'm going to do is I'm going to do one greater than control, and it's going to be 1 minus 1. Now, there should be zeros for every variable here, but that's a pain in the foot to type. So if you just hit submit, SPM will automatically, oh, blimey, that's hard to see.
Mhm.
SPM will automatically zero pad. What that says is 1 minus 1 and then an arrow, and then it says right padded with 11 zeros. Name defined, contrast defined. So you hit OK. And so now you have your first contrast, and it shows you what the contrast will look like. That's +1, that's -1. Do the same thing in reverse. Control greater than SCA 1. And this one's going to be -1, 1. Submit. And it zero pads it again. You hit OK. And if you have any other contrast to add, Otherwise, you hit done. Okay, masking. Now we've already done our masking, so we're fine. We're going to say none. We're going to use FWE, family-wise error correction, at 0.05. The other common way to report things, especially if you're a little less certain about your relationships, is an uncorrected p less than 0.001. But I prefer to use family-wise error. It feels more principled to me. And then extent threshold. So this is saying how many voxels marks a cluster. So you can say 0 to have it be literally anything, or what our current and what is common is to set that threshold at 100, just to sort of another sort of noise removal.
Yeah, for 1 millimeter anatomical data is around 100 voxels.
So these areas here are all the areas where it found significantly higher volume in control subjects compared to SCA1 subjects. Now there is this big area right here at the tentorium where the cerebellum is, and that's an artifact. Unfortunately, just the nature of the beast is when we're doing the smoothing, we wind up getting a little bit of cerebellum in there, even with the cropping. So we ignore that part. But you can see, it's a little hard to see on this. I might actually see if I can fix my resolution. But there's bits of each. Caudate is the one that's more medial, right? Yeah. There's pretty significant areas in the caudate, and then you've also got another spot up here. Which I think is in like sort of the premotor area.
It could be,
And at the bottom, it gives you a bunch of more specific information, like the centroid of each large cluster and statistical information about that. This, again, can be saved as a PDF or a MATLAB figure file or something like that. It also tells you your degrees of freedom, and it tells you the threshold of the t-value that represents p less than 0.05, which in this case is about 5.3. This is pretty typical for cerebellar data. Does anyone have any questions about this kind of idea?
I guess the only thing that I was gonna ask, you know, that area is not actually significant because you're only using gray matter in the cord, like
Yeah.
in the brain and not cerebellum, right?
Yeah, this is an artifact from the cerebellum. If we were to look at the cerebellar data, it would be lighting up like a Christmas tree. Couple of other things in this view. No, that's not what I want to do. You can save the thresholded data. So by default, as soon as you view a contrast, it will automatically save that contrast. It'll save a full T-map. So this guy here, this is the map of T-values across the brain for your second contrast, which is this one here that we're looking at. So we've got contrast 2, it's saved a nifty file, and it's saving the t-values. You can save a thresholded version of that by going to save, thresholded, and you could call it. And then it will save that out as well. And this one will remove everything that isn't significant. And then we can change the significance level we look at if we want to look at p less than 0.01 uncorrected. And we can swap over also to SCA1 greater than control. and see there's nothing significant. There are no areas in the brain where SCA1 subjects have more volume than control subjects in the cerebellar or cerebral gray matter. So doing that all through the GUI is fine once. But if you're doing a lot of analyses, you probably don't want to do that. So that's why going back to that, script. Yeah, so that is why I've taken those script pieces and I've pulled them out and I've put them all into the script file. So there's the covariates, the rest of the model setup. This is telling it to do the explicit mask that we talked about. This is the part that actually, this is a second job that actually tells it, all right, run the thing. And then at the end, I tell it to create contrasts. Oops, we changed our folder. And so here I've automatically specified, all right, these are the contrasts I'm interested in. Again, you only need to specify up to the last one, and then you can assume it'll put zeros on the rest. And this is all the SPM code to run it. And what it'll basically do is it'll just go through a loop and run every contrast you feed it. And what it does is it will actually save. I've told it to save the, that output we have
Expressed it out.
here. Nope. Nope. Yes, again. Wrong. Good grief. This one. Hey! It will automatically save this as a PDF, and it will automatically save the thresholded significant. Yeah, these are the flags right here. So this one tells it to save the, god damn it, tells it to save the thresholded stuff. And this will tell it to save the output as a PDF. And so we go over to what I got out with the analysis I ran with the scripts. You can see I've got the propped files here, and I've got the PDF files, and there's an error in the title, but it doesn't super matter. And you can see same areas, same data table, all that sort of stuff. So now that we've run the analysis, how do we visualize it? I actually do this on the Linux partition on my laptop because then I don't have to do this. And it's also just generally faster. Thank you. Okay. So I'm going to add standard, and I'm going to add an MNI brain. But and then I'm going to add as an overlay so you can see here, and I'm going to put this in a different color. There's our caudates. If we round up here, we'll find somewheres. There it is. There's our little bit over by premotor. Now, before I do this, usually what I'll do is I'll run a calculation of Cohen's d as an effect size. I have a script that does that, and I have a script that calculates a correlation coefficient from T-maps for regressions. But the principle is the same. You're calling up the statistical output, and you're mapping it on the brain, and now you can turn off the cursor, show a color bar, left, make the background white so that it doesn't cause issues with paper so much. And then you click the little camera button and you take a screenshot. And you can crop out the brains and pop it in a figure. The cerebellum is unique because you can get the cerebellum data onto just a regular brain map, but because the cerebellum is small and complex, this is where suit comes into play. So I'm going to go back to the batch editor, and I'm going to go into SPM, Tools, Suit, and plot volume on cerebellar flat map. So the cerebellum essentially has the same problem as like a globe, where you try to flatten it out, it's going to get a little weird. There it is. So let's find something cerebellar to map. Actually, let's put it up in FSLIs first. Where did FSLIs go? There you are. All right. So I'm going to go to my own stats that I actually did and show you what a cerebellar map looks like. So there it is normally, and you can see why we generally exclude anything right around the tentorium, because it very clearly looks like bleed over from the cerebellum. So that's how it sort of looks on the cerebellum. But if we want to see a little more clearly where it's at in functional areas, why am I in scripts? Stats, group-wise, seg1. And this guy. So we're going to plot it in suit space. We can change the scale, but I'm not going to bother here. And the threshold, so if the file had values from say -5 to +5, you could tell, okay, I only want positive values. You can change which color map you use. I usually use one called Turbo because it does a bit more gradual of excuse me, move from blue to yellow to red. And I've actually imported it into the version of FSLIs that I'm running on my laptop. Because I think in FSLIs it was, yeah, 0.6 to about 2.25. And then we hit go. Oh, oh, the hell on. Ah. No, I only want this one. I'm gonna close. Oh, nope. Never mind. We got it. Cool. Okay. So this is what a cerebellar flat map looks like. So running top to bottom, we have lobules 1 to 4, 5, 6, cruise 1, cruise 2, lobule 7B, 8A, 8B, 9, 10. And then down the middle, we have the vermis. So what you would see in this one is you would see, okay, well, we've got our strongest effects in lobules 1 to 4. And we've got weaker effects here in cruise 1 and 8B kind of thing. And so that helps, and in the vermis, so that can help you sort of anatomically identify where your effects are happening. This is something you can also save and also crop and also put in to figures. And I can show you what one of those, God damn it. I can show you what one of those looks like. From, where's our, of course I don't have a link to our bioarchive paper.
You don't? If you go to my website, it's there, but you don't have it there.
Hold on.
Or just go.
Aha! This is literally just a PDF of the Word file. Yeah, so this is one of the figures that is in the paper that was just accepted for publication. So you can see in the white matter, we've got a lot in the pons and the brain stem, and it's sort of reaching up towards the motor area here through like spinocerebellar tract and things like that. You can see the flat map here and how it corresponds with different parts of the cerebellum. I created forest plots to show sort of different regions have different effect size of differences between control and SCA subjects. And that all comes out of the stuff that I just showed you.
The flat map is just because sometimes it's hard to see, like in a structure, if you want to show everything. For example, if you want to show all the cerebellum, before we have the flat map, what you do is that you just show some kind of slides, right? So you have put there 10.
Yeah.
But when you have a lot of figures, then you cannot have like 10 and 10 and 10. So the flat map just basically take the cerebellum and open it like this.
Like an orange.
So you can see everything. It's not everything because it's not representation, right?
Yeah.
But you can see a little bit more in just one single image that just having to put all the different slides in an image.
Yeah. So then you can get away with, you know, 1 or 2 representative slices in each plane and your flat map. I'm rather proud of these figures. I spent a lot of time in PowerPoint making the numbers line up just so. And yeah, these are all different. So like this one, what we did is we separated subjects out by duration, higher or lower than the median, and repeats of the CAG allele in the affected gene greater or less than the median.
The duration is how long they have had the disease, and the CAG is like how strong is the mutation.
And this runs off almost identical code to the one that I showed you earlier for just the whole group-wise comparison. The main difference is we took out age and site and used pre-corrected data. But otherwise, everything else is the same. So,
Questions about the process? I think it was really clear, everything. Wow. Thank you, Jason.
thank you.
This is a really good tutorial. I hope that every one of you prepare something like this. I try to do it didactical, right? So we learn how to use the things that you're using. And yeah, like we can save these recordings somewhere so they are available if at some point you want to use it.
But can we get a flat map of the whole brain or just the?
There's also flat map for the brain. Usually it's just half. So you need to make a flat map for the left and one flat for the right, and then you have like two images to see everything. Right, because the medial part, it basically is where you open the brain and this, but just one hemisphere and then the other one.
That flat map will be only the cortex, or does it include in the midbrain or?
It's just the cortex. It doesn't include the cauda or the putamen or anything in the middle. Yeah, it's just the outer part. I think that you can stop the recording. Faisal, do you have any questions?
I'm good. Thank
All
you
right.
for the
Okay.
presentation.
All right, I'm gonna hit stop.
Well, like with the